Okay. Whenever you feel free, like you feel for it, we can start actually.
Mm-hmm,
I'm
mm-hmm.
recording right now. Yes, perfect.
Okay, who's ready for more ZK? ZKGM, everyone. My name is Milica. I'm DevRel engineer for ZK Verify and also doing PhD in zero knowledge proofs. Let me try share my humble presentation. Okay, today is not going to be easy, but I believe in you guys. We have been through quite some rides with cryptography and everything we had, right? And the hashes, like, and the ciphers and all the games we had. So I trust we're gonna have we're gonna have some ample understanding with further math. But yeah, today is going to be the day where we're going to dive in KZG commitments, but also we're going to show how to work with multi-party computations. What are actually zero knowledge proofs now that we had all the parts from the cryptography that we have covered. One thing that came to my mind that we can cover, and I can send you some links about it, is elliptic curve cryptography, which could be the crown of everything we had here. But maybe we can cover it in the next class as intro to snarks. But yeah, let's start with the properties and who are actually the actors in all of these ZKs, like let's see where's the zero knowledgeness in all of these things, right? Because we're constantly talking about how to trick hackers into not be able to read what we're trying to hide. So it's always some kind of with cryptography and zero knowledge proofs, it's always some kind of, hide and seek game in a way. So yeah, let's see who the actors are, what do they do, how does it look like, and I'll try to explain KZG, which will help you understand and see the zero knowledge in this part. Okay, before we dive into it, why ZKPs? Why? It's been shown I mean, like before blockchain, we didn't really use ZKPs. The blockchain was the machine that pushed ZKPs forward. Before that, it was sitting in the dark on a paper that people in the 80s have created. It's that old, older than most of us here in the call, I think. But sometimes if the industry does not pick up certain things, we're not going to see the development of it. So how did it come that we have ZKPs in the blockchain? So one of the first things that most of the people heard about are ZK rollups, where we're trying to see, like, how can we just put like thousands of transactions into one, as in a way to reduce the cost of one transaction. So instead of paying for one transaction, you will pay for 1,000th part of it by having a roll-up. And for that to be possible, we need to, with all the 1,000 transactions being run on some layer two, we need to enclose a proof that we did all of these transactions correctly, right? So that's where zero knowledge proofs come to light, and we have a spotlight on them for a couple of years due to that. Another thing is privacy. So you can have, it's not only that you're proving that, for example, you calculated all of the transactions correctly. It's also for hiding certain data. So it has that nice property, but usually when people say like, "Oh, it's using ZKP," doesn't mean that you're going to have the privacy property. It could be it's a very common misunderstanding with ZKs that the zero knowledgeness in terms of privacy is always included. But yeah, you can use it for that way as well. So how does it look like? So you see this nice save box, and like I can tell you, like, hello, I know the secret code to the save box, and you try to unlock it, you cannot because you don't know the secret password, the secret phrase, right? But I tell you, like, hey, I know that combination. And you would tell me like, prove it. And I would say like, okay, but I will not show you my secret combination because then it's not secret anymore, right? But what I will tell you is like, you can, write something on a paper that only you know what it is about. And you can slide it through this a small opening. And if I can read it, that means that I was able to open this safe box, right? And read it out for you. So that's something that we usually call interactive proof because you can say like, oh, you were so lucky that you just guessed the combination, which might be true. But if we increase the possibilities the possibility that I was able to just guess it, it's diminishing, right? So that's one of the examples that you can use and explain what is actually zero knowledge proof. So in this case, that would be the combination to a safe box. What do we use in ZK? Who are the actors, right? Whenever you have a story, you should know the actors, like the main actors are prover and the verifier. So prover wants to actually prove some statement that would be a subject. And the verifier would be like, hey, like, I need something to support it. So with that, a prover will have a witness, and there will be relation between witness and statement that the verifier will get. We'll see it in a bit. So yes, if we have, we just come back, S would be a statement, W is usually witness. That's how it's marked usually in ZKs. Witness is a secret part. Statement is something as in, hello, I know the combination of the say box. So yes, this is actually the basis basically basis in a way that hey, I want to prove that I have a statement and I'll close the witness as well, but I will prove the relation between the two without revealing my secret, my witness. So yeah, we have learned hashes a couple of classes ago. So one of the examples we can use is hash pre-image, where we can say, okay, I can tell you like, hey, I know such a number that when we hash it, we do the modulus 7, it will end up in 4. And that will be the statement, right? And the prover would say, okay, sure, I will ask you to prove it. So sometimes it's difficult to do it in a way to let's say like you can say like, okay, I know a hash of modulus 7 such that it ends in 4. But it's easy to just add on numbers in this case. But when you have to do it on a bigger scale, it becomes really difficult for a prover to do that if they do not really know the answer or they do not possess a group that has the answer to it. So, for example, how does verifier satisfies how is verifier satisfied with answer? So there is something that the verifier can do is they can add certain numbers up to in such a way that it satisfies that modulus ends up in 0. And they can say like, okay, I added this and it ended up with modulus 0. But there is a weakness in this that we have that it can be revealed and that a prover can learn about the original number. But yeah, it's this is how it goes. It says like, I know a secret number that has 4. Verifier says prove it, but don't tell me the number. Then prover can show some alternative valid number. It just can add the modulus to it, and the verifier can say like, okay, I trust you that you know these answers without showing me the one that you actually you want to hide. Because basically what we're proving here is that we can make such calculations that satisfies our statement. So yeah, let's try it out like we did before with pairs. So how many people are here? Let's see. There are like Barbie and I guess some AI. That there are 31 people if we do not count me. So let's make some pairs and let's make some calculations. You guys can say like, yeah, let's I'll tell you that I know modulus such as we can use modulus 7 or modulus, let's say 13. But let's divide in pairs. I don't know, Hatun, do you want to write pair couples or
Yeah, sure. Let me just check who wants to be with me.
okay.
No one?
Yeah, I'll be there.
Okay, perfect.
Okay.
Okay, let's write down because it's going to be difficult.
Yeah, it's good.
Okay, let's say Hatun and who's there? Almost. That's one couple. Ariel, Rocio. You know, guys, how to send private messages in this chat. So far, you know, super cool. Okay, Nisha, Carolina. Okay.
We are working with modulus 7, right? 7.
You can choose whatever you agree on.
Okay.
It can be between you guys. Just use a prime number. Oh, hello, Laura. Is there something who is not named for Paris? Someone? No one?
King right now.
Can you show again the previous slides with the example, please?
Mm-hmm. That's it.
Yes, thank you.
Okay, suppose that most of the people have communicated and tried. Why did Ariel scared Rosia with the secret number?
She just left the meeting.
No. Okay, how many of you have tried this successfully with your partner?
I think we did.
Sorry?
I think we did. Like,
Okay.
she gave me a number, I gave her, and like we tried to prove that it's satisfied.
Okay, so question from Carolina. So the verifier is supposed to prove that they know such groupation of numbers that satisfies that, let's say, modulus of 7 is 4, like in our example, like what we have here. That is the idea. Okay, that was one easy exercise for a plain prover and a verifier. This is what we had here is interactive proof where the prover can ask all the time the verifier like, hey, can you prove that you know a number that is a member of this group?
Just excuse me, I don't know, but I didn't understood even if it seems logical, but can we do it with an example that I pick so that I understand what we have to do? So
Okay. Yeah, let's try.
if I give you 15, what are you supposed to say to me or to verify? Or
Let's say that, for example, you have let's see this one. Let's say that hash of something
yes,
modulus 7 ends up with 4, because for a 15 you would need to find something that's bigger than 7. Otherwise you didn't do a modulus properly, right? Because 15 modulus 7 would end up in what? 1. So for this example, the main idea is to prove that you know such number that when you apply modulus of 7, you will end up with 4. That is the whole idea.
but what was supposed to say to me the other person? Like I don't understood the exercise.
Yeah, I'm not sure which part. Let's see.
Mirika, can you and Hatun do one example so that it is clarified?
Okay, Hatu has hands up.
Okay,
Go.
I was just going to like ask it. So I have a magical number, and in this example, let's call it X, and X mod 7 is 3. So I will send Melissa not the number, but I will send her that 52, for example, so that she can check whether my like, am I, correct or not. But my number is not 52, right? This is the right approach. Like, did I understand wrong too?
Okay, it should be that whatever you send, if you're not doing the padding, it would satisfy the statement. The statement is that the hash is 4.
Yeah, like I said hash is like 3 and I send you 52, but it is not my number. I just add multiple 7.
Yes,
Oh,
yes,
that
yes. Okay.
not understand my number. Like
Yeah.
I'm just saying that I picked 3. Okay, I'm revealing my secret right now. I
Okay.
picked 3, but in order to send to Melissa, I don't want to send 3, but I'm saying that okay, if I add multiple 7,
You end up 7. You added up 7 times 7, which is 49.
yeah, and I end up with 52, and I say, Melissa, this is not my number, but if you satisfy this one, you will satisfy my number 2. So it is like that, right?
Yes, that's it. Ariel?
Yes, I was having like the same question because I was expecting a kind of response from my partner. But then I just realized that you are sharing like a proof that you know a number in the curve. So for example, the curve is made by these 3 numbers, 108, 350, 482. And I'm sharing like, hey, I have this curve, this secret number that is part of this curve, that module 11 is equal to 9. But I'm not sharing what is my number. It could be like, for example, 31, that it's also modulus 11 equals 9, or even a graded number.
Yeah, that's it. That's it. You are you're not necessarily sharing your secret number. You're revealing some part of the group where like you say like, hey, for this one, I know the solution. And you know, this group can be insanely huge. It doesn't mean that you know, by this repetition you will end up actually showing that number, but you're showing that you know the answer to something. It's maybe not as intuitive in a way that, you know, like, yeah, but in the end someone will find out the answer, right? Because in the small group, it's that's why it's we're using some more complicated maths for ZKs, but this is how it's done. Usually the prover is asking like, hey, verifier, you know, if you really know the answer to this, you will show me something, like prove me. And like there are challenges, because in this example, for example, what Hatun said, I could say like, yeah, 52 modulus 7, yes, it will end up, let's say in 3 that you said it's going to be your hash. But I can say like, okay, Hatun was just lucky, and like next time she can provide 59, or next time she can provide 66. But I can say like, you know, Hatun is just lucky, and like by repeating this, I'm diminishing chances that she is lucky and that she can actually calculate that.
Okay, so the verifier has to keep providing different values until the prover and verifiers like find the same number.
So the prover has to check. It will not just accept per se, it needs to check. Does it satisfy the equation? So in this case, it's 25 modulus 7 that ends up in 4. So the thing is that prover has much lighter work than verifier is. The verifier does. So in this case, the prover is just checking one equation, while the verifier needs to the prover needs to has this hard work, where a verifier is just like checking at the end, okay, does this satisfy the equation what the prover sent? And the verifier would be like, okay, until the verifier is convinced that the prover actually knows something. Okay, we're gonna go through more examples. So we'll open questions later to see if we have actually covered this, or we need more examples or explanations. Yeah, so one of the things is like sometimes you want to add some padding, as in that modulus of whatever the prover sends ends up in 0. And in this example is like if we just say, okay, we're gonna send you 25, the verifier would know like, okay, so I will reveal part by part. But if we add some padding to it, for example, 10 35 modulus 7 will end up in 0 because it's perfect division in this case, so nothing is left after modulus. But yeah, if we say like, okay, our R is 10, it's easy for the verifier to calculate the secret number, and that's why we'll see in some of the examples how to use commitments. Okay. Yeah, we have tried this, so as we had like yeah, let's find the secret number that hashes to 4 and verify would say, yeah, prove it, but don't tell me the number. Prover can show alternative valid number. So let's say not 25, we can send 32 or 39, and then the verifier will be convinced without learning the witnessed or the secret number. Okay, so you can play with that like for infinite number of times, and the weight of the calculation is on the prover, that the prover constantly needs to prove itself, pun intended. And yeah, it's constant rounds like, hey, prove me you know something, and like it can go. It's really not that efficient. So we needed to go to work with other stuff, but that are non-interactive proofs, which we're gonna see later. But yeah, one of the nice examples is the graph isomorphism that you can see in this picture, where we were, let's say, proving the path that n2 is between n1 and n3 and all these relations, and all these graphs are true. So yeah, we have seen the non-interactive.
Sorry, can you go back to the isomorphism? I didn't really understand why it was important for the prover and the verifier.
Okay, so I can tell you that I know such a graph that satisfies the relations, and I can present it in different ways, and every time it will be the truth, that you will find a path through from one point to another, and all of these are practically the same picture. They're proving the same thing, but they're like presented differently, if that makes any sense.
Okay, and this is to reduce like the number of time the prover has to prove.
So it's not I wouldn't say it would decrease the interaction, but it's just one of the examples that we can see for the interactives.
Okay.
Okay. Super cool. Yeah, so we're gonna see something that's more exciting than interactive proofs, because with interactive proofs you can you can query many times. The prover for verifier can do that. For example, there are even 3D maps. That's something that's similar with the previous example, where I can say like, okay, I know such place in the map, like it's like three coloring map, and I can always say like, yeah, I know such a color that that doesn't repeat around itself, and it's provable by math. And then you can always say like, okay, but reveal it to me and reveal your neighbors, and you will just see always one part of the map, but the map can change, but my statement will not change. So I can always say like, yeah, but the map is true. And you always query it, and like if we have the same map, eventually you can learn all the fields. But if the map changes constantly, like in the previous example, the hash could change. Let's say like, yeah, I know how to calculate modulus. And you can say like, okay, prove me with modulus 4, prove me with modulus 7, 13, 11, whatever. And if I always give you the correct numbers or the correct coloring on the map, you will say like, okay, this prover knows how to calculate these values, right? But it's quite inefficient because there is always back and forth communication, and someone needs to check it. So that's why we have Fiat-Shamir transformation, and it's this part that we're going to see later is used for blockchain. Yeah, let's do another exercise. We're gonna do it with multi-party computation. You will see it often in documentations, especially if you're reading some white papers that people are using multi-party computation. So what does that mean? That means that, for example, there is even a secret sharing part, but it means that actually like everyone who joined computation will take some part of it, and in the end no one would be able to determine a secret part. Why is it interesting? It's interesting because, for example, you can calculate, you know how usually companies are saying like, okay, the salaries we have in the company are kept secret, and for example you want to know what's the average salary in your team, but you do not want to reveal your own data. You just want to find what the average is as a team. And what you can do is, because you want your inputs to stay private, everyone can just learn the result. Let's say there are 5 of us, and all 5 of us we're adding up our data, and the public result can be divided. We're gonna look at it, how it's calculated. Yes. Okay, for this exercise, we need all the participants. We can, because we had a birthday attack last time, we can calculate our ages. We can calculate the average age of all of us. So how does it look like is that I would need a couple of volunteers to do this, because I don't think we can do it as efficiently with 32 participants on the call. So let's say we have 10 of participants. Okay. I will start. Okay. Oh, there's some questions. Sorry. Okay. Aha. So Rocio didn't just leave Ariel. It's Ariel, you see, your number was not that scary. Nothing is scary for Rocio, hey? Okay. So, okay, so there is okay, we need 10 participants. Who's in? Write in chat. Harry wants to join. Okay, so this is how we're going to do. I will write down. So I will give my number to one person. That person should calculate and add their number, etc., etc. Let's see. But how to send it privately, I will send messages. Yeah, someone just revealed their age. Fine. I will send private message to that one person, and that person will send a message to others. Let's make a kind of a chain. So I will send my number to Hatun. She will send it to Reed. Okay.
Here's something. That random offset is going to be different for all of us, or the same.
I will be adding the random offset, the first one.
Okay, but in my turn, should I add my own random offset too?
No, you just add your age.
Okay.
The first person will add the offset, but because I'm not tracking the computation, I will not be able to know each of your private inputs because the person you're sending, let's say that you are the first person that is having input from me. You will not be able to find anything about my secret input because I have the secret offset and you add your age, but because you're not sending that back to me, I cannot read it. And the next person will not be able to read what's in because we got like the mixture of two sacred inputs and one random offset. Okay, I will just make so like what we will do is I will send my secret input to Hatun. Hatun will send it to Hatun will add her age and send it to Reed. Reed will add his age and send it to Madhu, etc., etc. Okay. Let's see if we're going to have something. Okay.
So Milika, tell me one thing. So the last number will come up to you only?
Whoever is the last in chain
Oh, yes.
sends it back to me.
Oh, okay, fine.
Mm-hmm.
So then you'll be subtracting the offset that you have earlier added, and
Yes.
that's how not average, but the number will be revealed.
Yes. So Luaka will send the number back to me because if the last number is public and the offset is not subtracted, then Hatun will be able to compare the two inputs and find out my secret input. Here. So Hatun, I will send you my secret input. Let the games begin. Any doubts, you just ask.
So only the last person will know the offset, right?
Yes. I mean, the first one and the last one with the chain. Okay, while we wait for the other participants, may I just say how vibrant is Milan office here?
That's awesome. The office also looks perfect.
Yeah. I love it here.
Is it a WeWork?
Yes, it's a
Yeah,
WeWork.
I thought so.
Where are you right now? In Milan?
Yes, where our engineering team works tirelessly. Okay, I have received a number from Luaka. Okay. Yes, it is a beautiful place. And we have really nice sunsets. I love it. So, we have 296. Yeah, 296 as our number in the end. And we have to divide it by 12 because there are 12 participants. So what is that in the end? What's our average age? Almost 25. 24.6666. Do you guys think it's right? Everyone who participated. Do you feel like you're around that age? That we got it right?
Define around.
Okay, super cool. We got it. That's MPC, guys. That's multi-party computation.
So interesting because it is so easy, but it works really fine. Like it's so interesting.
Yeah, right? It's like people are like using it all the time, and people are like, okay, does everyone knows what is the offset? Who would know what's the offset? Maybe yeah, the last person who's getting it. First and last, only if the last person is publishing. Yeah. Because I would say like, okay, this is the result, because if I subtract my offset and divide it, that's the secret is retained. Super cool. Yay! Nothing got leaked except that John published before we started. Super cool. Okay. Yes, so the group is hiding the inputs, only reveals the results, and the witness is also hidden with ZKP. It's revealing only the statement truth. And yes, we have a privacy preserving computation. Let's look at properties of zero knowledge proofs. Does anyone have strengths for it? No. That we had a couple of computations and waiting times. Okay. So there are three things that we need to satisfy in order to be able to call something a zero knowledge proof. It's completeness, soundness, and zero knowledge-ness, to say so. And it means that we do not know anything about the input. So with completeness, it means that if the statement is true, an honest prover can always convince the verifier. So if we know how to calculate the modulus, we'll always be able to calculate it and convince the verifier that we know how to use that function. When the with the soundness is that if the statement is false, there is no way that we, as someone, if someone wants to cheat, right, a cheating prover, there is no way for a cheating prover to prove and trick in the end the verifier into accepting the proof, because the verifier will be always checking it, right? So there is no way. With interactive proofs, there is always like a diminishing chance that this can be done. But with multiple rounds, it's that chances are like, let's say like, if we have the result, it's like 0 or 1. And in the first round, it's if it's like 0 or 1, it could be the result. And let's say the correct result is 1. In the first round, it will be 50%. In next round, it will be 25%, then 12.5, etc., where it's 1 through 2 to the power of rounds. Will be the chance that actually the person is just being lucky and is able to trick it. With the third property, the zero knowledge-ness, it says that a verifier cannot learn anything beyond the fact that the statement is true. With that, thus protecting the prover's secret information, and the prover's information is not leaked, and no one can say anything about it. That's one of the, I suppose that many people here in this group, when they hear about ZK, usually the first real world use case would be like, oh, you can prove you're of certain age without actually showing all the data from your ID, right? Or from a passport, but you can just say like, hey, I have this passport, but I'll enclose the zero knowledge proof that says like, okay, I'm over a certain age and I can enter this club, or I can buy certain drinks or something like that. Why do we have polynomial commitments? We're going to see how it looks like to calculate them. It's in the beginning, it looks a bit scary, but actually it's not. If you go through it a couple of times, you will see why is that, because you are practically just repeating the same order of things, and we can try it with some equations that are quite simple. But let's say that you know, the prover can learn something out of it with time. We'll see about it. But yeah, so the properties to commitments is like, yeah, I'm committing to, let's say, some equation. And I will tell you like, okay, like every time you ask me about it, I will tell you like for the value on x axis, I will be able to tell you like the exact value of that function, the exact point in the system. So the properties are binding, hiding, and succinct verification. Why all of that? So binding is like you are like always you committed to that function, and that's the property of binding, because you are using that as to stay true to that one function. Like that's the binding. It's like always that one input that you have will always end up at the same point, let's say in the XY system. And hiding is, of course, that you do not reveal the whole function. Successness is that you can check it easily. So yeah, let's go through one another example. Like, who's excited for this?
Malika, before we could proceed ahead, I still didn't got the binding part. What exactly? So what do we do exactly in binding?
You'll see through the example. So we can say like I don't know, Hatun, do you want to make couples here? To let's say like, okay, like anytime, I mean, like maybe we don't have that much time, or like let's see what else is there. Okay.
Person can do it as a theatrical way, like not all of us, but maybe we can, something like that, so that it won't take a lot of time.
Oh yeah. We don't have to do it together. Do you see, guys, the chat before we started MPC? There were pairs.
Okay.
We can use the same pairs, so I don't have to write them.
Okay, yeah.
So there is Hatun, Almas, Ariel, Rocio. So the idea is to pick your polynomial. Polynomial meaning like you have one function, and that verifier can ask the value, let's say something on x-axis, it can be -1 or something like that, and the prover will just real it. By the end of, let's say, a 10th challenge, you will be able to see the function, but you will not be able to completely reconstruct it if it's something much more complicated, right? That easy. So let's try it. I know you can use polynomial as 3x plus 2, minus x minus 1, be creative with it. And then the verifier can ask, and prover will reveal certain dots on the grid coordinate system.
In these cases, x is always prime number, right? You are mute.
Sorry, it doesn't have to be. It needs to be something. So it's like the equation in coordinated system. So x can be whatever number. So a verifier can ask a prover, like, give me your result in this point. It can be any point on x-axis.
Can I ask you something?
Sure.
Like whenever like I reveal something, for example, it says it asks 3 and I say it is 30. What does that mean? Like they don't understand my function and what the value that I reveal means. Like how they can check whether, I'm telling the truth or not. Did I ask correctly or not? But I don't know. Like I don't understand the reason. Like right now in this example, prover reveals 11. So like what happened? Like with 11?
It's the result in the 0.4.
Yeah, but like
Malika, here the equation is already there, so we calculate. That is okay. What Hatun and I or we are trying to understand, like suppose I give x as a value, and Hatun is revealing the final output number, something as 30. Now that equation, so do we need to crack, how we can crack that equation part, or what exactly we are expected here? We are confused about that aspect, the process, what we are expected of. Because we are not revealing the exact, we can say, equation, just sharing the numbers. So do we need to come to a point to an equation or something else? Hope I clarified that.
Only like asking values and the results, right? That's it.
Yeah. That's it. That's it.
Okay.
Okay, so I see the questions in the box, and what would be the answer is that you bind it to the polynomial, committed to a polynomial, so you cannot trick the verifier finding another polynomial that satisfies the result. So we did the exercise to show how it goes, but basically you are binding with the polynomial that you cannot just abandon it and say, we will not, we just decided not to use this anymore and we're binding with something else, or like we are leaving this polynomial in a way that, I'll just find another equation that satisfies the result. Okay, I see the questions of how to bind the polynomial, where they are. We'll see how one of the famous commitment schemes look like, Goldberg, and we'll see how they do the calculations. How do we use the binding mechanism? Where is that polynomial? Who has it, right? And all of the rest of it. So far, I just wanted to show you how the calculations look like behind the scenes. How does the mechanism work? Back and forth with the proving with the numbers, right? And calculating some function. So I hope that everyone did it in the pairs already. So yeah, the polynomial is bounded with the prover, and we're gonna see how does trusted setup look like. There are zero knowledge proofs without trusted setup, and that's why they say they're quantum resistant, and that those with the trusted setup are not quantum resistant. We'll see all of it in a bit. Just let me share it. Okay. I hope you can see see people nodding, so super cool. So KZG is something that's the backbone of zero knowledge proofs so far. It's a commitment scheme named after Kate Zavarusha and Goldberg. And that's we'll see pairing in it. How does polynomial commitment look like? How does binding work behind the scenes? What is commitment, and how to prove you know certain value without revealing without revealing your secret in the beginning, right? Okay. The key properties of it are that it's compact, efficient, and that it has trusted setup. Why do we have all of this? It needs to have structured reference string. We'll see in a bit how does it look like. The verification is very fast. You will see that it's constant size, commitments, and proofs, which is a very nice property when you look at the trace of the proof in the end, and it's not increasing by it's not increasing with the inputs. It's rather a constant size. And let's see how it looks like and how this polynomial setup look like. So first of all, to have a polynomial, you need to have a structure that looks like this one, like P of X, and then you need to have X to the power of, it depends on the order of your polynomial. In this case, it's order of n. So you will have at certain place, you will see like A0, it's binded with X0. So because anything to the power of 0 means 1, we just have the constant here. And with the polynomial, the coefficients are secret. So in our case that we had, we were supposed to have secret coefficients, but because we do not have a commitment scheme, we cannot do it as efficiently as KZG commitment scheme does. So you want to commit to some polynomial, and you want to later prove that whatever is given to you, you know the result, as we did in the previous example, because we were able, let's say, Hatun was able to tell Ariel, okay, I'm committing to this polynomial, and I'll prove you that I know it by providing you the results to it with the challenges you give to me. The trusted setup is made by a group of certain order. Usually it's group G or for order P, and we'll see in a bit how to generate one of those. How do they look like? How do we choose them? And the G's that we have are generators of the group. So you can think of them as value in the beginning that we're using to construct the whole group. that will be used to calculate points in our functions, right? We will see it in a bit how everything looks like because we have an example. Yes, if we have trusted setup leaked, right? If we have the S leaked, which is a part of structured reference string that we see here, then the security will diminish, which we cannot allow. And yeah, these structured reference strings, they can be universal, they can be per circuit, but yeah, wherever you can, you should have one per circuit. It will increase the security. Let's go to the procedure. All right. So the KZG consists of a couple of steps. We will see how does setup look like, how does commitment look like, evaluation, and verification. So first of all, you need to create this secret group of yours, this trusted setup. You need to do the commitment to a certain polynomial, right? Using your setup. And later on, we will evaluate the result and later on verify it. So let's say that this is our group of order P. What does it mean? That the number of participants and the number of elements in the group can be a maximum of P. Let's say it's 7, it will end up in 7 members of the group, right? This is how the setup is done. This GP that you see, it's the calculated group, and then once we have tau, which is that secret, it needs to be deleted. But so far, you see that we have G. G is a member of one of the elements of group G. So it can be anything from 0 to P minus 1 times G, okay? And then whatever we picked for trusted setup, we will multiply it till the order of D, which we'll see it's the order of our equation. Till then, we will calculate the GP because we can even calculate more of it, but it doesn't really make sense for us to go over and have H's for a bigger order than our polynomial is. This is how commitment looks like. So we are committing this GP, this group that we have, HO, H1, H2, etc., till HD, with the function where whenever we calculate the function in these areas with tau, we'll get something that sorry, this is. Okay, I'm trying to read, to be able to read everything and still have the camera set up. So this is how it ends up in the commitment, because we're going to do calculations with secret numbers. Okay, so every part of our polynomial, every degree of our polynomial will have enclosed H. So for the constant in our formula, in our polynomial, will enclose H0. To the order of 1, we'll have H1. all up to the order of D. Let's go through an example. Let's say we have group from 0 to 6, meaning that the order is 7, and we will say that the G is a generator of the group, and we will pick 1 because it's much easier for us to calculate, right? P that we have seen, it's a field of the it's a field of order of B. This is our polynomial x to the power 2 plus 2x minus 1. And let's say that we're picking tau, the secret number we're picking up as 5. And because our D, the order of our polynomial is 2, we will be able to calculate the GP, and we will remind ourselves how. Just let me check if there is anything that is unclear. Check. Okay. Okay. So let's remind ourselves, how do we calculate our polynomial, the commitment of our polynomial? We can do it like this, but first of all, how do we calculate the group, right? This is how. So first of all, H0 will become G. What we see from the top part is that G is 1. H1 will be tau times G, because tau is 5. We will end up with the number 5. In H2, we will see tau to the power of 2 times G, which is 25 times 1. But because we have the order of 7, it will end up in 4. I don't see it right now. Is it? Yeah, it's written 4. Any questions so far? Okay. So this is the commitment. This is how we actually commit to a polynomial. We're using the previous values that we got, H0, H1, H2, that we calculated using tau and G. And we're calculating all the points within our polynomial. Can someone jump in for this exercise? Who would like to volunteer? See, Ariel?
Monica,
Yeah.
in the last example, H2 was 25. So how come the H2 is written as 4?
Because
Given that the number is
because our group order is 7. So we need to do modulus.
okay, fine. That's fine.
Because once you have the order, everything needs to be, all the results need to be within that group. Hatun, do you want to do the first example, which with F0?
Yeah, I can try. So here, I don't know how to, I don't know my steps, I think.
Okay.
Needed for
Well,
me.
let's go through it together. So we have F0 times H0. let's see if there is something that we can use for us to help us. Let's go back to definitions. Where did we define it? Okay. So we will use age 0, right? Which in our example before was 1.
Oh, I see now. Okay.
Yeah.
Okay. So in the first one, the H0 was let me just check.
1.
It was 1. In the second one, it was 5, and the third one it was 25. But since we get the modulo, it is 4. The F values, we are putting 1. For example, we are putting 0 at the beginning, so it is -1.
Yes, because that is the order that we start with. Yes.
Okay, in the second one, we are giving 1, and it becomes 2, and
Because it's
we are
2
going
times x.
that way. And when we calculate the result, it is 13. We are getting modulo. So I don't understand why I don't understand why we're calculating these stuff. I'm sorry if it is too fundamental.
No worries, because we want to show in the end how can we hide our trusted setup, because once we calculate everything within our function and give it to the verifier, they will not be able to deconstruct the tau, but they will be able to say that we have the right polynomial. They will come to the same result basically.
Oh, so they will have hash values, but they don't have the tau, right?
Yeah, we can look at that way. Yeah. Maybe this is a bit too advanced for the group. Yeah, maybe we can wrap it up soon due to yeah, well, it's maybe I have maybe we haven't planned this that much, right? Because it seems like it's too advanced a bit. But yeah, if nothing, I will give you the whole calculation that everyone can sit down and calculate. And yeah, I don't expect it's gonna be in one sitting that everyone can understand KZG. But I'll just show you how to calculate it right now. And then I'll just enclose the whole calculation with the commitment and verification and evaluation so that you can check it and compare it. It's a bit, it can be tricky a bit.
That would be amazing.
I have a question.
Yes.
To calculate F2 times H2,
Yeah.
or it's written H3, but it's H2, or it's H3?
Let me check. I don't see it. Yeah, it's actually it should be H2. It's my mistake.
And so F2 times H2. So F2 would be 2 times 2 plus 2 times 2 minus 1. So we get 7. And then we multiply by H2, which is 4. So here we...
No, I think you must multiply with 1, not 2. Like -1, 2 times 1, plus 1 plus 4.
But how do we calculate F2, basically, is my question.
Yeah, so what we have here is we're using the coefficients. with F0, F1, F2. We're using coefficients. That's why we have respectively -1, 2, and 1. And we're multiplying them with H0, H1, and H2.
And how do we get 1 for F2?
1 for F2, because in front of x to the power of 2, there are no coefficients, so we're implying that the coefficient is 1.
Okay. Okay, so F2 is the coefficient in front of the power of 2.
Yes.
Oh, that makes sense. So right now, we don't have to reveal tau, but since they have the coefficients and they have the ash values, I can calculate any values and we can check. Like, I don't need to reveal that value, but we can, you know, agree on the value actually is correct. Okay.
This is what the commitment part is. But yeah, for it to be calculated, it needs to use the what we have made with generator and trusted setup later. Just check. Here we can use commitment with F with the point in tau, meaning 5, times G, the generator, which is 1. And because it needs to belong to the field of G where we got the generator from, we need always to be at the same in the same field, in the same modulus. And we need to do modulus 7 because our P, the order of the field is 7. So what we can do is we can calculate the polynomial in 0.5. That means -1 plus 2 times 5 plus 5 to the power of 2. That will end up in 34. With modulus 7, it will in 6. This is how we do the check.
And the check is done by the verifier or by who?
This is so far because we have in this part, wherever you see tau, this it cannot be done by a verifier. So verifier should not know anything about the secret value. It's just for us to check. This part is for us to check if we did everything well. But if we did everything well with starting from H0, H1, and H2 values, we should have the same result. It's done just for the internal check. It's
Okay.
done usually, right? Yeah. Yeah, it's a bit advanced. It looks a bit complicated. I'm trying to make it as simple, but still it's like, there are fields, there are new terms that we have. What is how to react with the chicken in a shell. Oh, but yeah, it's this is deemed as a foundation of zero knowledge proofs because it's you will see the secret value what actual binding is, how can you check it, because you see that we have used our polynomial with calculated h0, h1, and h2 and got the same exact number as if we had used just tau, the secret one that we were supposed to delete in the beginning, but we were just like, we're going to keep it just to check it later. This is just for the example. But yeah, it's a lot of new it's a lot of new terms that we have, and yeah, then the order of the group, the group itself, how do we use it, and like thousands of questions, and like why do we need to be within the same order? But yeah, that's what we have with the KZG, which we'll see that there are foundation for snarks like GROT16, etc. But yeah, I will send you guys the check, the verifying and evaluating part of this exercise, because we sadly do not have that much time, and I would like for you guys to repeat the process. I'll just put it, the complete calculation in the chat, so that you can repeat the process. And please, if you have time, please do it. I'll be there to answer all the questions, because doing this on the class with this advanced topic, we will not get this far, but we need more time than we had. So let's then stop here. And yeah, the prover will never be able to know tau. And yeah, is it math or magic? Who knows? Mr. Bean has definitely, provide gave some bigger answer to contributed to the age in MPC computation. So where we use KZGs is mostly with the ZK circuits, the Merkle trees, and with rollups. And yeah, let's go with the summary for now. We're gonna stop here. Later on, we can work through verification evaluation. We have seen the witness, the statement, the relations, the prover, the verifier. How do they work? How do interactive and non-interactive proofs work with multi-party computation? The key properties of zero-knowledge proofs, which are completeness, soundness, and zero-knowledge-ness. And how do commitments look like, and KZG, which are the zero-knowledge proof foundations. And then for the next class, you will look at the calculations and polynomial commitments that I'm going to send in the chat for you guys. And then if needed, we can have one shorter session just to try and calculate once again everything that we have. But I think it's a bit too much for one sitting. After 2 hours, I don't think anyone has the concentration to sleep.
Melika, can you just put the previous slide where the use cases?
Yes.
I had read, I think it's EIP 4844 is also one of the things, right? I actually wanted to know if you can put some light on that, and because I've heard that KZ there is used for that.
Which one? Sorry.
EIP 4844. Ethereum Foundation's proposal.
Yeah, I will send. If you can just write in a Telegram group and tag me, I will send all the details about it.
Okay, sure, I'll do that.
Okay, perfect.
Today was really intense, by the way. Like,
I'm sorry, but
no, it was amazing. Like, I can feel my brain is growing. So,
I'm sorry. I know it's sometimes this is too much. But yeah, if you guys want to understand ZK's in depth, yeah, like Hatun, we can organize some session between today and Wednesday just for wrapping up the KZG, because for KZG I think we would need another 45 minutes for everything to go through. But yeah, first of all, I would like you guys to work through the examples I sent. And also for what Saurav asked, I will provide answers for that as well. But for after the KZG, you will see the Grot 16 and Plonk and Starks. And yeah, for the building together, you can always join our Telegram group for ZK Verified Dev. Follow us on Twitter or now X. Visit our docs. This is me on Twitter, ZeroX Milica. And yeah, like stay building, stay curious with ZK. And yeah, honestly, Hatun, if you want, we can organize some session tomorrow or Wednesday where we can go through more details on KCG.
yeah, sure. I'm gonna text you and we can arrange maybe.
Yeah. Tomorrow I think I'll be at Politecnico di Milano. I'll know by the end of the day which day exactly with the professor. That yeah, it's I see that people are interested, but then the attention is not here anymore.
By the way, I try with different polynomial and I get the correct results, like the commitment and like, yeah, like trying another example with myself helped me a lot. Like I got it. I got
Yeah, you see, it's like it needs to start somewhere so that people can try it out on their own and they see like, okay, every time I check it with tau, whatever my tau is and my generator, it will end up in the same result. So it's a good start.
eureka moment for me, like, oh yeah, it is working. So yeah, let's just
Yeah, eureka, right?
yeah, people gonna love it.
Yeah. Yeah, we need definitely one additional class for this so that we can see like, oh, what is actually binding property? How do we prove we know something without telling them that we know something? And what are those numbers that we're actually sending?
Thank you for this session. By the way, it took literally 2 hours and like
I didn't get any water.
yeah, by the way, I just drink tea. But yeah.
Oh, this feels good.
Thank you very much. Seriously.
Guys, I hope you're not too discouraged with this session. But yeah, let's continue working on let's continue working
I
on
have
PCG.
I have a question, Milika. I just wanted to know what are the like real use case where you think this commitment case actually will be used, or is just the theory part? Because honestly, I'm more interested in the application part, or is it going to be useful for me as a developer, as a builder? So,
For this, it's why do you need to know KZG as a developer? Actually, like there is nothing that you actually need to know um, per se, like when it comes to if you just want to do application part. Sometimes like you don't need to know. You just want to do application, you just want to use zero knowledge proofs, you want to verify them. You can say like, okay, I don't need to know. But there will be certain parts where you want to write a circuit and you don't know what private inputs are, like how does everything work behind the scenes. And if you want to know, what is the hiding property, how does it work? Do you want to use some other curve? Do you want to use some other type of proof? proof, you would need to know such properties, because how else can you tell, like, that certain curve is not for you, that certain type of proof will not meet your standards and your wishes and what you want, because let's say it exponentially grows. With this example, you would see that it's always constant one. So those are the things that if you want to learn how to develop applications using zero-knowledge proofs, it's not mandatory, but if you really want to be good at what you do, you should definitely learn it.
Actually,
Thanks, Monica.
No worries.
I wanted to write Merkle tree, but I couldn't because after the Ethereum roadmap, I saw there is something called Merkle tree, and I said, hey, maybe I can do it. It must be another data structure. I couldn't because I didn't know, I didn't understand Pedersen commitment, I think. But I'm gonna just check it out after this class. Maybe I can understand finally.
Yeah. We need to wrap it up with the verification evaluation, and then you'll see. But it's as if you learn any kind of math, you need to do repetition. That's why they have one class and like a couple of repetitions, but to try it out with different examples. But yeah, guys, I'll send you everything. Thank you for having me. Thank you for staying at the end of the lecture. Hope you will read what I send you.
I believe everyone gonna read because it was really interesting.
Okay, it will be even more interesting.
I think we don't have any additional questions, so we can finish. We took Melissa's 2 hours, and maybe we can just finish right now.
No worries, it's 2 hours gladly given for ZK. Anything. Yeah.
Can we go to cry right now?
It's okay. We were in that spot. Like I was when I first saw ZK proofs, I said I'm not going to touch it with the town foot poll, and here I am.
Yeah.
So it looks frightening, and that's why we started with some smaller examples with some intros, so that this, when I throw ZK proofs with as a KZG, it's not that intimidating, because you went through Diffie-Hellman, you went through hashes, you went to some older ciphers, some modern ciphers, you've seen it as a preparation, but still, like, now you are prepared, but we just need more time to go through everything slowly, that that groups are not new for you, that orders are not new for you. Now that we have come to this point, then we'll do the evaluation and verification part as well. Okay, guys.
Thank you for the session, and hope.
Thank you very much.
Yes, thank you so
Bye.
much.
Yeah.
See you
Thanks,
Wednesday.
Melissa. Thanks, guys.
Thanks,
Yeah.
Malika. Take
Bye.
care. Bye.